Okay. So, all right, everyone is here then. Yeah. Okay. Okay. So let's start then. So, am I the host? No. Yes. All right. So let me just remind you a bit of what we were doing last time. So we were talking about symplectic forms, right? So the first thing is what is a symplectic vector space? So it's a finite dimensional vector space together with an alternating bilinear form, which is non-degenerate. Okay. And we saw a prototypical example of how to construct a symplectic form. So on R2n, which you can identify with Cn, you take the operator j, which is multiplication by I from Cn to Cn, so that j squared is minus identity. And then you define a bilinear form. Omega of Vw is the usual real inner product, Euclidean real inner product between Jv and W. And this we saw was alternating using the fact that J is an isometry for the inner product and J squared is minus identity. And we also saw that this was non-degenerate using the fact that the inner product is non-degenerate and J is an isomorphism. And then we express this alternating bilinear form in terms of the standard basis of R2n. So how do you get the standard basis? You first take the standard basis E1 to En of Rn. So this is an orthonormal basis of Rn, which you identify with the subspace of Cn consisting of all real vectors, vectors with all coordinates real. And then you let Fi be j times Ei. So F1 to Fn is a basis of IRn, which is the subspace of Cn consisting of all vectors with all coordinates purely imaginary. And together E1 to En and F1 to Fn, they form an orthonormal basis of R2n. And with respect to this basis, we calculated the alternating bilinear form omega applied to these basis vectors. So on Ei, Ej, it was 0. On Fi, Fj, it was 0. And on Ei, Fj, it was delta Ij. So from that, we get that when we write the two form omega with respect to the basis of alternating two forms, so that's given by wedge products Ei star wedge Ej star, Fi star wedge Fj star, and Ei star wedge Fj star. So then because omega applied to Ei Ej and Fi Fj is 0, the coefficients of Ei star wedge Ej star and Fi star wedge Fj star will be 0. And for Ei star wedge Fj star, the coefficient will be delta Ij. So that means omega becomes sum over I, Ei star wedge Fi star, right? Okay. And the matrix of omega with respect to this basis E1 to En, F1 to Fn is the block matrix 0 identity minus identity 0. Okay, so this is a skew symmetric invertible matrix. And then we said a manifold was a symplectic manifold if you have a two form omega on the manifold such that on each tangent space, omega is non-degenerate on each tangent space. So each tangent space is a symplectic vector space and omega is closed. So d omega is 0. So then we define the Hamiltonian vector field of any smooth function on n. So that was using the isomorphism between the tangent space and the cotangent space, TPM and TP star M, given by the alternating, the non-degenerate bilinear form omega. And so any smooth function H gives you at each point an element of the cotangent space DH at P, and that corresponds by this isomorphism to an element of the tangent space, which we denote as XH at P, by XH at P. So that gave us a smooth vector field. And then we saw that this smooth vector field, any Hamiltonian vector field XH, it preserves the symplectic form omega, because the Lie derivative using Cartan's formula, we saw it was 0. LXH of omega was 0. So that means that the flow phi t star of omega will be equal to omega for all t. And we also saw that omega is symplectic if and only if omega power n, that's a top degree form. The dimension of n has to be even. So 2 times little n for some integer n. So omega was simplex, non-degenerate if and only if omega power n was non-zero at all points. So omega power wedge power n is a volume form on n, and the flow of the Hamiltonian vector field preserves this volume form. Okay, so Hamiltonian vector fields they preserve the symplectic volume form. Okay, so they're volume preserving flows. And then we contrasted this, and we also saw they preserve the Hamiltonian function h, right? So that means the integral curves will be contained inside level sets of the Hamiltonian function. Okay, the integral curves will be contained inside level sets. So as an example, we took the standard symplectic form on R2 dx wedge dy, and then we looked at the gradient vector field. It was just a radial vector field for the function h equal to half norm squared, and the Hamiltonian vector field was minus j of the gradient vector field nabla h. So it was the gradient vector field, this radial vector field rotated by 90 degrees clockwise. So the radial vector field moves outwards along straight lines. The Hamiltonian function h increases along the gradient vector, along curves, integral curves of the gradient vector field, whereas the Hamiltonian vector field moves along circles, which are level sets of the Hamiltonian function h. It preserves the function h. And the flow of the Hamiltonian vector field is a flow of rotations. So rotations preserve volume, right? So it preserves the form omega. Okay, the form omega is dx wedge dy. It's the volume form on R2 in this case. Okay, and so then we saw that the tangent bundle of a Riemannian manifold, this becomes, well, this has at each point an alternating 2 form, which is non-degenerate. So to do that, we use the decomposition of the tangent space to the tangent bundle into horizontal and vertical components, right? Identifying it with TPM, direct sum TPM. And using that, we defined what's called an almost complex structure on the tangent bundle, J, which sent a tangent vector with horizontal and vertical components xi h, xi v to the pair minus xi v, xi h. And so it's easy to see that J squared is minus identity, and J is an isometry for the Sasaki inner product on the tangent space. And so we could define, like we did for R2n, using the multiplication by I and the Euclidean inner product on R2n. So similarly here, using this J and the Sasaki metric, we defined a 2 form, an alternating 2 form, omega, which was Sasaki inner product between J xi and eta, right? So this is alternating and non-degenerate. What we're going to show today is that omega is closed. We haven't showed yet that this is a closed two form, right? So for a symplectic manifold, we need the two form to be closed. So in fact, we'll show that omega is exact. Okay. So the last thing that we showed was that if I look at omega wedge power n, then this gives us the Riemannian up to a constant n factorial. This gives us exactly the Riemannian volume form of the Sasaki metric, because by the construction, like we did in R2n, if you take an orthonormal basis E1 to En of the horizontal subspace H theta of the tangent space T theta Tm, and you let Fi be J theta of Ei, so then F1 to Fn becomes an orthonormal basis of the vertical subspace, because this J, it interchanges horizontal and vertical subspaces, right? It sends horizontal to vertical and vertical to horizontal. And it's an isometry, so an orthonormal basis of horizontal goes to an orthonormal basis of vertical. And because Fi is J of Ei, and Ei's are orthonormal, then the same calculation as in R2n tells us that omega can be written as summation Ei star wedge Fi star, right? And so when you do omega wedge power n, you'll get n factorial E1 star wedge F1 star up to En star wedge Fn star. And this last 2n form, this is nothing but the Riemannian volume form of the Sasaki metric, because this applied to the orthonormal basis E1, F1, E2, F2, En, Fn, this gives 1, right? And that's how you define the Riemannian volume form on a Riemannian manifold. It's the volume form which gives 1 on every orthonormal basis, on every positively oriented orthonormal basis. Okay. All right. Okay, so is everything okay up to here? Yes?
Yes.
Any questions? Okay. So then today let me start with something I might have talked about earlier. I don't remember. So let me just recall it. So let's look at the notes for a second. So there's a notion here of what's called related vector fields. So okay. So here's the notion. So let phi from M to N be a smooth map between smooth manifolds. Then we say that two vector fields, X on M and Y on N, these are said to be phi related. So we denote this by X tilde phi Y. If for all P and M, d phi at P applied to X of P is the same as Y at F of P. Okay. So in this picture, here is a point P in M, and you're looking at a tangent vector XP, the vector field X at P, and the derivative of phi at P is supposed to map X at P to the tangent vector Y at phi of P. Okay. So then we'll say that these two vector fields are phi related. Okay. So if I draw this picture a bit more, then these tangent vectors of X at these points, these should go to tangent vectors of Y at these points, at the image points. So what do you think will happen to the integral curves under phi? What should happen to integral curves?
They should map to the integral curves of Y.
Right. So it's like joining the dots, right? So if I join the dots here, I'll get the integral curves of X. And since phi maps tangent vectors of Y, X to tangent vectors of Y, when I join the dots, it should map integral curves of x to integral curves of y. Okay. That should be obvious from the picture. Okay. So in this case, it looks like phi is a diffeomorphism, but this is one example. But phi can be a submersion also. It can be like a projection. So for example, if I take a cylinder, and on this cylinder, I take this horizontal vector field, whose integral curves are horizontal circles in the cylinder. Okay. And then I just take a projection to the circle, right? This cylinder projects onto a circle S1. Yeah, so this cylinder is, say, S1 cross R. R is the vertical coordinate. And this projects to S1. And this map phi is the projection to the first coordinate. So then this horizontal vector field above, it projects to the natural vector field on the circle below, right? So these two are phi related, but phi is not a diffeomorphism anymore. It's a projection, right? And in fact, the vector field above, there are many vector fields above which project to the same vector field below, because above, I can just take any vector field whose horizontal component projects to the vector field below, and the vertical component can be anything, because the vertical component under d phi, it projects to 0, you see. So this vector field above, which is a sort of diagonal, this will also project to the vector field on the circle below. You see this? Yeah, I can make the vertical component in the cylinder anything I want. Is this clear?
Yes.
Okay, so these are examples of these are examples of phi related vector fields x in chi m, y in chi n, x is phi related to y, means that d phi p xp is equal to y phi p for all p in n. So here, what should happen, for example, if I look at this picture here, then flowing along an integral curve of x here and then projecting should be the same as first projecting and then flowing by y below, right? You see that? So this diagram should commute, right? If I flow by the flow of x and say I come here and then I project, right? That should be the same as first projecting and then flowing by y, right? Yes?
Yes.
Okay. So that's what the next proposition says. So So this is the basic proposition about phi related vector fields. So let phi be a smooth map from M to N. X is a vector field on M and Y is a vector field on N. Then the following are equivalent. X is phi related to Y, 1, and 2, if F is a function, a smooth function on N, then if I look at F composed with phi, this becomes a smooth function on M. So if I look at X applied to the function F composed with phi, this is the same as Y applied to the function F, and then you compose with phi, okay? And finally, what I was saying about the integral curves, that phi composed with phi tx is the same as phi ty composed with phi, right? So this means phi composed with phi tx means first you flow time t by x, then you apply phi, you project. That is the same as first projecting, applying phi, and then flowing by time t under y, okay? So these three are equivalent. So let's quickly prove this. So 1 implies 2. So suppose x is phi related to y, and let's take a point P in M and a function f, a smooth function on N. So then if I look at x of f composed phi at P, by definition, this is the derivative at P of f composed phi applied to x at P. So by the chain rule, this is df at phi of P applied to d phi at P applied to xp. And since x and y are f related, we're assuming 1, which is x is f related to y, phi related to y. So then d phi p applied to xp will be y at phi p. And then I'm applying df to this. So this by definition is y applied to f at the point phi p. Is this clear? Yes?
Yes, yes.
Okay, so 1 implies 2. Now we show 2 implies 1. So we're assuming this condition, x of f composed phi is yf composed phi. So we have to show that x is phi related to y. So let P be a point in M, and let alpha be an element of the dual, the cotangent space to N at the point phi P. Okay. So then we can choose a smooth function f in N whose derivative at phi P is equal to alpha, right? This I can do. Yes? Because alpha I can write as a linear combination of dxi's, where xi's are coordinates near phi of P. So it's some summation alpha I dxi. So that's the derivative of alpha I xi, right? D of alpha I, summation alpha I xi. And then summation alpha I xi is smooth in a neighborhood of P. So I just multiply it by a bump function, which is 1 in a neighborhood of P and 0 outside some larger neighborhood of P. That extends it to a smooth function on all of N, whose derivative at P is still summation alpha I dxi, right? Is this clear?
Yes, sir.
Okay, so we can find such a function f. Now I use the given condition. So let's look at alpha of the vector y at phi p, right? So y at phi p is an element of the tangent space at phi p in N. So alpha acts on it. So alpha applied to this is df at phi p applied to y at phi p. So that's yf applied at the point phi p. Now by hypothesis, yf at the point phi p is equal to x of f composed phi at the point P. And this is the derivative of f composed phi applied to x at P. So by the chain rule, that is df at phi P applied to d phi at P applied to xp. And df at phi P is nothing but alpha. So this is alpha of d phi at P applied to xp. So that means for any element of the dual space of T phi Pn, alpha applied to the vector y at phi p is equal to alpha applied to the vector d phi at p xp. Okay, so since alpha, this holds for all elements of the dual, so then the two vectors have to be the same, right? If all elements of the dual space give you the same applied to two vectors, then the two vectors have to be the same, right?
Yes.
Okay, so alpha was arbitrary, so therefore y at phi p is equal to d phi p of xp. Okay, so that proves 2 implies 1. And now we prove 1 implies 3. So if x is phi related to y, then phi is what's called a semi-conjugacy between the flows, right? So if phi was invertible, then this means that I can take, if phi was invertible, I could take this phi to the other side and I would get phi tx phi inverse is equal to phi ty. That means that phi would conjugate the flow of x to the flow of y. But in general, it doesn't conjugate. It's what's called a semi-conjugacy, right? So like in the example of the cylinder and the circle, there it's not a diffeomorphism, it's not invertible, but it semi-conjugates. Okay. All right. So let's prove 1 implies 3. So if I take a point P and M, if I look at the curve phi composed with phi tx of P, so this is a curve in Y. So let's look at its derivative. So ddt of this will be d phi at the point phi tx of P applied to x at the point phi tx of P. And since x and y are phi related, this will be y at the point phi of phi tx of P. Okay. In other words, the derivative of this curve, if I call this gamma, then ddt of gamma t is equal to y at the point gamma t. So this curve gamma t, this is an integral curve of y, right? This is an integral curve of y, and the initial condition at time 0, phi composed with phi 0 x of p is just phi of p. So this is the unique integral curve of y with initial condition phi of p. And so therefore it must be given by applying phi ty to phi of p. It must be the curve t goes to phi ty of phi of p, right? So that proves that phi composed with phi tx is equal to phi ty composed with phi. Is this okay? Yes?
Yes, sir.
And finally, for 3 implies 1, if we're given that phi conjugates the flows, semi-conjugates the flows, then we just differentiate this equality at time t equal to 0. And so that's what we're doing here. So we look at d phi at p applied to x at p. So by the chain rule, this is ddt at t equal to 0 of phi composed with phi tx at p. And phi composed with phi tx, we're assuming is equal to phi ty composed with phi. And when I differentiate this at t equal to 0, since phi ty is the flow of y, I will just get, this is an integral curve of y with initial value phi p. So this will give me y at phi p, right? Is this clear?
Yes, sir.
Okay. All right. So that proves this little proposition. And as a corollary, we get that if I have 2 vector fields x1, x2 on M and y1, y2 on N, such that xi is phi related to yi for I equals to 1, 2, then the brackets are phi related. So x1, x2 is phi related to y1, y2. So for that, we use condition 2 of the previous lemma, of the previous proposition. We have to show this holds for every function, C infinity function on N, x of f composed phi is yf composed phi. So we have to show this for the brackets. So we look at y1, y2 applied to f composed with phi. So this by definition is y1, y2 minus y2, y1 applied to f composed with phi. So this is y1 of y2f composed with phi minus y2 of y1f composed with phi. Now, y1 of any function composed with phi is the same as, because y1 is phi related to x1 by property 2 of the previous proposition, this is the same as x1 of y2f composed with phi, right? And similarly, the second term, y2 of this function y1f composed with phi, because y2 is phi related to x2, this is the same as x2 of y1f composed with phi. Yes?
Yes, sir.
And then we use this property again, that y2 of f composed with phi, because y2 is phi related to x2, this is the same as x2 of f composed with phi. And similarly, y1 of f composed with phi is the same as x1 of f composed with phi. And so what we get is x1, x2 minus x2, x1 applied to f composed with phi, which is bracket x1, x2 applied to f composed with phi. Okay, so this proves the property 2 for the vector fields bracket x1, x2 and bracket y1, y2. Okay, so the brackets are phi related. Okay. Is this clear?
Yeah. Yes.
Yeah. Okay. So, I mean, if you want to see this visually, geometrically, what's happening is what is this? Okay. So yeah, if you want to see this visually, what's happening is that this is P and you're flowing by x1 and then by x2. What is the bracket? It's an infinitesimal commutator, right?
Yes, sir. Yes.
So you're flowing by x1, then by x2, then by minus x1, and then by minus x2. And this little bit here, this is bracket x1, x2. Now when you apply phi, phi semi-conjugates the flow of x1 to the flow of y1, right? And the flow of x2 to the flow of y2. So phi will map this picture to a little quadrilateral starting at phi of p, where you'll flow by y1 and then you'll flow by y2 and then by minus y1 and then by minus y2. And so, and phi, I mean, d phi will map this little tangent vector to this little tangent vector here. So that means that d phi will map bracket y x1, x2 to bracket y1, y2. Is it clear?
Yes.
Yeah. So xi phi related to yi, I equals to 1, 2, implies bracket x1, x2 is phi related to bracket y1, y2. Okay. So now the next thing to talk about is Riemannian submersions. Okay. So what is a Riemannian submersion? I defined this earlier. So let me give you the definition again. So a smooth map between Riemannian manifolds M to M bar is a Riemannian submersion if, so we define a subspace of the tangent space called the vertical space at P, at a point in MP. So nu P is defined to be the kernel of DF at P. So we assume this kernel is non-zero. Okay, this kernel is non-zero, and we also assume that if I look at the orthogonal complement of the kernel of the vertical subspace, so that's called the horizontal subspace, then DF at P restricted to the horizontal space, the orthogonal complement of the vertical space, this mapping to the tangent space at F of P of M bar, this is an isometry. Okay, this is an isometric isomorphism. So it's an isomorphism which is an isometry as well. Okay, so the subspace is nu P, which is the kernel of DFP, and HP, which is the orthogonal complement of nu P. These are called the vertical and horizontal subspaces of TPN. Okay, so we've seen an example of this, right? So here's a Riemannian submersion. Okay, so we've got less than a minute, so I'll just write the word and then end this meeting, and then we'll start the next meeting. Okay. So I'm ending this meeting.